Numerical integration. In this section, we will study a new method of approximating areas under curves. Just like we did with rectangles at the beginning of this chapter, we will use trapezoids here to do a slightly better job. So the objectives are to approximate a definite integral using trapezoids, and for intervals of equal length, use the trapezoidal rule to approximate a definite integral. Approximating areas under curves like we did in section 5.1 can be more efficient using trapezoids instead of rectangles. Example: a plane is flying in a straight line. Use trapezoids for the information provided in the table about the plane and explain the meaning of your result with appropriate units. We have a list of times in minutes and a list of velocities in kilometers per minute. So the first thing we want to do is to represent this on a graph. We have 5 points, the point 0, 10.1, the point 3, 11.2, the point 10, 10.5, 12, 12.1, and 16, 11, which I represented here, 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 and there. Note the y-axis break. The plane wasn't really changing velocity that much, but I did that so that we can see the trapezoids better. These 5 points create 4 trapezoids, and we will want to find the area of each of them and add them up. The area of a trapezoid is h times b1 plus b2 over 2, b1 and b2 being the base. In this case here, as you can notice, the height is actually horizontal. b1 and b2 will be the vertical values. The area of the first trapezoid here is therefore 3 times 10.1 plus 11.2 over 2. Then we repeat the same with the other 3 trapezoids. The second one has a height of 7. It goes from t equals 3 to t equals 10, etc. When we add all these terms up, we have 176.7. So what is the meaning of this number? Very often you'll need to express that in the AP exam. 176.7. When we integrate the velocity function, we are finding the area under the curve. We get the displacement of the object. Here it's a plane, it could be a particle, whatever. So we found the displacement of the plane, and clearly the plane was only going in one direction, so the displacement or the total distance is the same. And the units is kilometers, so here is the full answer. The result gives the displacement of the plane in kilometers during the 16 minutes of the flight provided in the table. The plane travels 176.7 kilometers during these 16 minutes. There are 3 informations that are very important that you have to write down every time. They are the 3 information that AP will look for. First is the meaning. What did we look for? We found the displacement of the plane. Then you need to express the units. Here the number is in kilometers. And finally, you need to give the limits. Here it's just 16 minutes. Sometimes you could express it as between t equals 0 and t equals 16, or you could say during the first 16 minutes of something, but you need to give the lower bound and upper bound. So meaning, units, and limits of integration. The trapezoidal rule is a rule that works only when we have trapezoids of equal length. So in the example above, the plane, we had t equals 0, t equals 3, t equals 10, so it was not partitioned in subintervals of equal length. When it is, we can use this formula here. The area is going to be h over 2, where h is the length of one trapezoid. h over 2 times y0 plus 2y1 plus 2y2, etc., plus 2yn minus 1 plus yn. So we have a factor 2 everywhere except for the first and the last of these terms. Trapezoids must all have the same width to use the formula. Another note of interest is that the trapezoid will always give you the value of the left rectangular approximation plus right rectangular approximation over 2. We will prove this here in the homework. So use the trapezoidal rule with n equals 4 to approximate the integral below under the graph of y equals x squared between x equals 1 and x equals 7. This is y equals x squared between x equals 1 and x equals 7 using 4 subintervals. So our trapezoids here that I tried to represent in pink, and we can discuss the quality of my drawing later, they all have the same width. It's 1.5, 1.5, 1.5, 1.5, so I can use the trapezoidal rule. The area under the curve is going to be approximately 1.5 over 2 times. So what is the height here? It's 1 squared, it's 1, plus 2 times 2.5 squared, plus 2 times 4 squared, plus 2 times 5.5 squared, plus 1 times 7 squared. So this is all the f of x, f of x, f of x that we multiply by 2. We add all of these up and we get an area of 116.25. The exact area under the curve is 114. So we have an over approximation. Actually, my trapezoid should be above the graph. I didn't do that very well. I wanted us to be able to see the trapezoids, and I didn't do it very well. One thing about AP exams, if you leave an answer like this without putting the result in this form, they will still give you full credit, so you don't need to actually go further than that. Simpson rules is another method to approximate an integral, but we won't be studying it, so even though you see it in exercises, always ignore it. Let's have a look at the objectives again. Approximate a definite integral using trapezoids, that's what we did here, and then in the case when trapezoids all have the same length here on the x-axis, we can use the trapezoidal